All right, welcome everybody to session 3 of Tuesday. Our first speaker is David Jes Myers from Johns Hopkins, who is going to tell us about double categories of dynamical systems. We'll have time for questions at the end, but if you have a question in the middle of the talk that you feel is quick and urgent, then feel free to raise your hand or type that into the group chat on Zoom, and may bring it up with the speaker. All right, take it away, David.
Thank you very much. So I'm going to be talking about dynamical systems today. This is going to be another talk in the series of talks about lenses or using lenses that we've heard today. So it's going to be sort of a general framework for putting together various sorts of lens-based dynamical systems. And it's going to use the technology of index double categories. So in order not to prematurely frighten anyone, I only called the talk double categories, but we'll see that secretly I was talking about index categories the whole time. But that's getting ahead of myself. So let me start with talking about what a dynamical system is to me in the course of this talk. So a dynamical system is going to involve two notions. It's a notion of how things may be, which we call the state, and a notion of how things will change given how they are. And that's what we might refer to as the dynamics of the system, or sometimes the update. But the dynamics of a system are not just determined by the state and how they will change, or how it will change is not just determined by how they are, but also some free parameters we might set separately from what we consider to be the state. And the system might expose some variables of the state. And the reason it will expose these variables is because those variables of its state might set the parameters of other systems. So we have some systems, say rainwater flowing over a hill, and the amount of rainwater that is at the top of the hill might depend on the amount of rain falling from the clouds. So if we have this dynamical system telling us about the flow of rainwater over the hill, its parameter, which is the amount of inflow, might be set by the exposed variable, which is the amount of outflow of the cloud dynamical system. And so the big things I'm going to try and do in this talk is give a notion of doctrine of dynamical systems. So there are a lot of ways we might specialize this very general definition of dynamical system. We might say, what sort of changes are possible in a given state? How do we specify a change? So should the dynamics of the system be deterministic? Should they be stochastic? Should they satisfy some properties, like should they be linear? Should they be continuous? Should the time vary discretely or continuous in other ways? How does the system vary with parameters? There's a bunch of questions we might ask when we're trying to make precise this very general notion. And a single answer to all these questions is what I will call a doctrine. So a doctrine is when you say I'm working with a discrete time dynamical system, the maps are measurable, and so on. That's a doctrine of your dynamical system. So the plan of this talk is I'm going to give a formal definition of dynamical system doctrine, and I'm going to define their two category, and that's a lie. I'm just going to tell you they have a two category. And then I'm going to define a dynamical system in a given doctrine, and I'm going to describe the ways that you can compose them by plugging variables into parameters, and I'm going to describe maps between them. So you've already seen Giorgio's talk today about exactly how this way of plugging in dynamical systems into parameters using wiring diagrams. I'm going to go over that again. And indeed, this is very much a talk in that program of dynamical systems. And then we're going to see a theorem. So I'm going to prove that trajectories, steady states, and periodic orbits, and other sorts of representable invariants of dynamical systems, that when you take these of coupled dynamical systems, so the dynamical systems you get by plugging in variables of some into others, that these features of them compose via matrix arithmetic. And this is going to generalize David's work, which has the nice title, The Steady States of Coupled Dynamical Systems Composed According to Matrix Arithmetic. And we're going to say yes and. Any representable feature of a dynamical system will compose via matrix arithmetic. And this is something I think is nice. So a lot of times in applied category theory, we talk about composing systems. But category theory began with the composition of maps. And the reason we like maps is because they let us define representable functors. So here we're going to see how both of these sorts of compositionality interact. And that's why we're going to use double categories. So I'm going to start with the definition of dynamical system doctrine, which is a bit intense. So I'm going to start with a few examples. So what I would call a deterministic automaton, and it might be of many sorts. So the actual action might be discrete, it might be continuous, it might be measurable. But in particular, a deterministic automaton has a discrete time. The next state is determined by the given state and an input symbol. And every state exposes an output symbol. So in particular, we have an input alphabet I, we have an output alphabet O, and we have a set or space of states and these two functions called the update and the readout. And so we've seen this definition a number of times today. I think Toby used this. I think Jella mentioned this, I believe, as well. And this is the exact same definition of a discrete time dynamical system. So we also have Markov decision processes, which are used very common, or what one might call a stochastic automaton. So the dynamics is given by saying the probability of transitioning to another state conditioned upon the current state. And maybe some other bits of data, like sometimes we get an expected reward for making this transition. This is often used in machine learning. And so the next state may depend also on an action taken by an agent. And the action is generally considered to be a free parameter. When we solve the problem associated with such a Markov decision process, it's usually to figure out which action maximizes reward, but that's separate. That's which parameter do we plug in to maximize reward. And so a Markov decision process is going to consist of a set of actions and a set of states and a stochastic function like this. So it's going to take in a state and an action, and it's going to give a probability distribution on rewards, which are real numbers, and a new state. And you could also have an output here. I didn't put it in because usually when people talk about Markov decision processes, they don't. But the output is generally useful. My further definition will include the output, but it's not common in the literature, so I didn't put it in here. So in a first order ordinary differential equation, the dynamics are given by specifying the tendency of change that the system has in the current state. So the equations often involve coefficients or other free parameters, and some variables we may choose to expose as external. So in full, if we have n state variables, k parameters, and m exposed variables, then our differential equation, we're going to need this vector of functions to put on the right-hand side of our differential equation. And we're going to get that. It's going to be a function of both the current state and the parameters. And so it's going to have that signature. And then our differential equation will be the derivative of the state in time is equal to this function valued at that state with that parameter. And we're going to have a readout function that's going to extract our exposed variables. So this is a simplified version of the kind of definition explored in Schultz, Bibek, and Vasilakopoulos. So their paper, they do this in a more general setting, but it's the exact same notion. It's just a special case, so it looks more like my other ones. Okay, so I'm now coming to the definition of dynamical system doctrine. I'm going to check my time here. All right. So this is a very abstract definition, and it captures all these cases and more. And so what it is we're going to have an index category of bundles. So why do we do this? Well, we need a category of spaces. So that's going to be C, because we have a notion of state space. And then we also need a notion of changes in a given state and a notion of parameter that's valid in a given state. And so being valid in a given state is going to mean that the parameters are going to be fibered over the exposed variables, really. And the changes might change depending on the state you are. So for example, the tangent bundle, which is really where the value of the right-hand side of a differential equation lives, it's a vector in the tangent bundle, might change over the base point. So we need this notion of bundle. And so we get that by having an index category. And then we need a notion that says, okay, if I'm in this state, what are the possible changes I can make? And so that's going to be a section of the Grothendieck deconstruction of this index category. And what that's going to do, so in other words, it assigns to every space a bundle of possible changes. And I call it T, and I'll think of it as the tangent bundle. But it's often quite trivial because, so a good example of this is if we have any strong monad on a Cartesian category, then we get this kind of weird index category, which is the bi-Kleisli category. And the case I want you to think about the most here is if the strong monad is the identity on the category of sets. And then this is just the co-Kleisli category for a given set. So this is a map from C times some set out. And the section is going to send every set to itself. And what that says is that if you're in a state, you can transition to any other state. The possible changes you can make are just another state. And if we change this monad, we change the kind of automaton we get. So for the identity monad, we get the deterministic automata. If we took the power set monad, we would get a non-deterministic automata. If we take the probability monad, we get a Markov decision process or a stochastic automaton. And if we use another monad, say if we want rewards, we can use this distributive law to get this other monad. And basically, you can put any kind of monad you really want in here. And one nice thing about this series of doctrines is that it's very easy to write it down in Haskell. So that's a plus. And the other example is very similar, except the section is changed. The notion of bundle of changes or tangent bundle. So if we work on the category Euc of Euclidean spaces and smooth maps between them, of Rn and smooth maps, then we still use the assignments sending everything to the Kleisli category here, which consists of maps that involve this extra data of the actual sort of state space below. But the section now is not going to be just trivial, it's going to take the derivative on a map. So this is one interesting thing where we get a completely different doctrine, like the difference between a deterministic automata on Euclidean spaces and a differential equation, first order ODE on differential equations, on Euclidean spaces, is just the change of section. And in fact, it's just how that section acts on morphisms. So this is the notion of dynamical system doctrine. And there's a two category of these. It's sort of the follow your nose definition. I'm not going to really talk about it, but the morphisms are like changes of doctrine. And so they're quite useful, but I'm not going to talk about them here. I can talk about them more later. Okay. Are there any questions so far? Okay, moving on. So here is a definition. It's due to David in his paper, Generalized Lens Categories via Functors of this sort. It's what Toby was calling a Grothendieck lens earlier. And so given an index category, we'll define a Bun map to be a map in the Grothendieck construction. So this is a pair of maps of the sort listed there. And so they go in the same direction. You go from B to B prime and you go from E to E prime. But then a Bun lens or a Grothendieck lens is going to be a map in the Grothendieck construction of the pointwise opposite. So this means that the map still goes from B to B prime. But then on the other hand, the thing up top goes backwards. And this is the pass back of information. And this is really useful because this is going to let us talk about plugging in variables into parameters. So one thing to see immediately is that the dynamical systems I was talking about before are all examples of lenses. So here is a particular, here's the definition of a dynamical system in a given doctrine. It's a lens of this particular form. So on the left, we have the bundle of changes, TS, sitting over S. And on the right, we have what I will call the interface. It consists of the parameter bundle I sitting over the outputs or observables of the system O. And being a lens means that we have two morphisms of the sort R from S to O, and then U from the pullback of I back over to S into TS. And so what that pullback means is, one thing is if our parameters change based on the output of our system or what our system was exposing, then this would mean that we're only allowed to take parameters that are valid in the current state we're in. So that's just a nice sanity check. But otherwise, what it has to do is with composition. It turns out to be useful there. Even so, for example, in the examples with the Koch-Kleisley, which I haven't said about, these all the examples I gave are just these specialized to this case. And there, it turns out to be useful for composition, which I'm going to come to now. So is there any question before I go on? Okay, so now let's talk about combining and mapping dynamical systems. So first I have to answer a basic question, which is why would I use double categories? Aren't categories enough? This is twice the headache. Well, there are two kinds of composing happening when we study dynamical systems. So first, we have maps between dynamical systems and their functions, so we can compose them like functions. But next, we have the compositionality of dynamical systems. So the systems themselves can be put together to form more complex systems. And we put them together by plugging in some of the variables of one state into the parameters of other systems. So a double category is a category with two sorts of morphism and a notion of commuting square between them. So for us, the commuting squares will look like this. Our objects will be systems, and the horizontal morphisms will be our maps between systems. And the vertical morphisms will be the blueprints for composing systems. And the squares will basically say that we have two ways of composing systems. We have a maps between all the constituent systems. When we have a commuting square like written there, when we can put those maps together to get a big map on our complex composite system. So let me show you what I mean by composing systems. So let's suppose we have two animals, foxes whose population is F and rabbits whose population is R. And they're governed by these these differential equations, namely that foxes are born at a rate BF and die at a rate DF, and similarly for rabbits. And now here is my blueprint for composition. I'm going to say that the rate at which the rabbits are dying is proportional to how many foxes there are, because presumably the foxes are eating the rabbits. And the rate at which the foxes are being born is proportional to how many rabbits they eat. So we can put them together and get this combined system by making those substitutions. And the combined system, this is called the Lotka-Volterra predator-prey model. And it's given by this wiring diagram. And this is the same wiring diagram we've seen a couple times today. And so let me tell you how this works with lenses. So here's that exact situation again written with lenses. Here's our Fox's dynamical system. And you can see that up top, we've written the expression of the dynamical system in terms of this function into the tangent space. And similarly with rabbits, our diagram now can be interpreted also as a lens, and you can see it's a lens of a particular simple sort. It just shuffles around the variables and maybe scales them a bit. And then our composed system is given by a composite of lenses. And this is a composite in the normal Grothendieck construction way. So that's very nice. That lets us put together our dynamical systems. And are there any questions with how we're doing this? One interesting thing of why we might want to do this is, for example, so I couldn't really fit this on a slide in a way that looked nice, but one thing we're probably all thinking about right now is this global pandemic. A common model for a common epidemiological model is the SIR model for susceptible, infected, recovered, or removed. One might imagine a multi-city SIR model where you have a bunch of different cities, each of which can have population flowing between them. And so their populations might grow and shrink according to how much population is flowing in and out. And each one of those is running their own SIR model. So you might wonder, how do we plug this together? We have a map of all the cities and the way they compose. We have a bunch of SIR models, one for each city. We want to put them together to get a larger map. And maybe then we can study, if we constrict the rates at which flow between cities happens, how does that affect the overall amount of infected and so on? So this is one reason we might want to study these couplings of dynamical systems. And we've seen others earlier. So practical reasons coming from engineering as opposed to epidemiology. So next, I want to talk about maps of dynamical systems. And the reason that I'm interested in maps is because they allow us to talk about what a dynamical system represents. So often we have these certain very simple dynamical systems, which are sort of shapes that we want to see drawn into other dynamical systems. So for example, we have the real line, and that is our image, our pure image of a trajectory. And we want to place that line in all our other systems in such a way that it actually flows according to the dynamics of that system. And that's what we would call a trajectory or a solution for that system. So a trajectory for a system will be, we have to choose the parameters at every time. So that's, I'm looking at the diagram right here, the square on the left right now. And we have to choose I. So at the bottom, you see that map I, that's a choice of parameters. We also have to choose a choice of output here, but it will end up being determined by our trajectory. So I'm going to leave that out of it. But once we have a choice of parameters, a trajectory is going to solve the differential equation I've listed below. And so, in other words, the derivative of the trajectory is going to be given by the change specified at that point with that choice of parameter. And so this equation below can be seen as a sort of commutation condition of these squares. And indeed, I'm going to show very soon a double category in which this is very true. These are the commutative squares in a certain double category. Another interesting thing we want to find in dynamical systems are steady states, states that aren't changing. So given a particular parameter and given a particular output we might want to look at, we can inquire at the steady states. So these are the states which in that state and in that parameter, there is no change, or their change is zero. Or, and I'm doing this in the dynamical systems doctrine, this makes sense in other doctrines as well. So in a deterministic automaton, this would just be a state that transitions to itself. So these are the two kinds of composition, these are the two kinds of morphism in the double category I want to get at, and these are the two kinds of composition that are happening in dynamical systems. So are there any questions before I go on? Okay, I'm going to go on. So now I'm going to come to indexed double categories of dynamical systems. So why indexed double categories of dynamical systems? I thought I was making double categories of dynamical systems. I had these two sorts of morphisms I wanted. Well, as it turns out, I really want to keep track of the interface of my dynamical systems. Because after all, I need to know that interface in order to be able to change it using a lens. So in order to be able to plug in exposed variables into parameters, I need to know what my exposed variables were, what my parameters were. So I want a category of dynamical systems for every interface. So the way that I can have a family of categories that varies over a double category is an index double category. And by that I mean, for those who know, a unital lax double functor. From a double category into the double category of categories, profunctors, and functors, with the profunctors horizontal. So what we're gonna build is an index double category of dynamical systems. So the way that's going to work is to every interface I/O, which is the sorts of variables we're exposing O, together with the sorts of parameters we're using I, we're going to get a category of dynamical systems with that interface. And then for every lens, we want a functor that takes an I/O dynamical system and plugs in, does what the lens says. The lens says plug this into that, and gives us an I prime O prime dynamical system. And then finally, we need to be able to change our interface. So if our category of dynamical systems with interface IO, these morphisms are going to preserve the interface. But in order to talk about trajectories and steady states and stuff, we need to change our interface. So the interface of a trajectory was the real line. So we need to be able to change that. We need to be able to choose a path of parameters. But we want to have the freedom to choose our parameters first. So the way I was talking before, if I go back 2 slides really quick, it looks like the definition of trajectory I'm giving here is gamma and I, this pair of choice of parameter and a path that satisfies this equation. But usually I have the choice of parameter in mind first, and then I ask, what are the solutions? And so that comes out naturally of this index double category, because to every horizontal morphism, I'm going to associate a profunctor. And that profunctor is going to take these 2 objects, or these 2 dynamical systems, and give me a set. And that set I can take to be the morphisms, the maps of dynamical systems that act in that way on parameters on the interface. So this is my base dynamical system. My base double category. It's going to be what I call the double category of interfaces. It's very much, it's a double category which merges together the Grothendieck construction, which you can find horizontally, and the Grothendieck construction of the pointwise opposite, which you can find vertically. And the commuting squares here are precisely the commuting squares. So if you take this diagram, there's only one way for this to commute. And if you write down that this commutes, that's the one I want. So this is going to be the arena in which all of our work is going to take place. So now our indexed double category of dynamical systems in a given doctrine is going to take an interface to the category of IO dynamical systems. And so the objects of that are these lenses into IO. And the morphisms are these squares in my double category of interfaces of this form. So they are going to be maps on state spaces that commute. In other words, they preserve, update, and readout. And to every lens, it associates the compose with a lens function, functor, which tells us how to glue together dynamical systems. And to every bundle map, which would go horizontally in a square that looks a lot like the one drawn on the page, it associates all the maps that fit into that square up top. All the maps on states that fit into that square. So this construction, even though I haven't quite mentioned it here, this construction is too functorial in doctrine. And moreover, not only is it too functorial, that construction preserves products. So cis is a 2 functor from dynamical system doctrines to index double categories, and it preserves products. And what's really nice about this is that I didn't talk about monoidalness, but I've been drawing these boxes floating together separately. And that floating together separately of those boxes is really a monoidal composition. As we've seen throughout many of the talks so far, monoidal product is used to talk about 2 independent systems considered together. And so that's equally important here. But luckily, by showing that this is too functorial and that it preserves products, I didn't have to do all the extra work of figuring out how this works for monoidal everything. It just follows through by 2 category theory. So I thought that was very nice. Okay, are there any questions on this construction before I go on to the theorem?
We have a quick question in the chat here. I think there's some. The question is that the TS and S. How does this fit into the double category of interfaces? Is that an interface, or how is it related to an interface?
Good. Yes, the TS over S is an interface. So by being a section of the Grothendieck construction, T, I write it as, it really should be written just as TS, not TS sitting over S. I'm sort of abusing notation there, but T takes a space and gives you an interface, or also known as a bundle. And in fact, the way this proof works is through a very abstract construction. that we just consider the T as a double functor from a horizontally considered state space category into the double category of interfaces, and then we apply a sort of slice construction. So it's all very formal. I don't know if that
I
clears
think
anything
part of the
up.
confusion was that when you have a dynamical system, it consists of TSS, which is the state space, and then IO, which is the interface. But now both of those pieces are also called interfaces because they live as objects in this double category.
Yes, yes. So for convenience, I like to keep the double category of interfaces quite large because it makes this formally go through very smoothly. The proof goes through very smoothly. But one thing to point out is that where the TS over S is appearing is only in the cat part of this index double category. All the things that live in interface, the indexing part, are always called IO. So even though it's an object of that category, because the objects of that category are just bundles from Bun, I'm not using it the same way I'm using the interfaces. Although the fact that it can be is what allows this to hum very smoothly. Okay, I'm going to go on because I think might be running out of time soon. So I want to here. So representable index double functors. So I'm going to try and say how various things can compose. So if we have a wiring diagram, like I was showing before, you can get a matrix. And using that matrix, you can sort of multiply that matrix by a vector of trajectories of steady states, maybe more literally then, and of other things. If you're working with finite automata, these things can be really finite. If you're not, I need to explain what I could possibly mean by having a vector of all trajectories and a matrix that you get out of this very infinite system. So what I really mean here are matrices of sets. So this is a common tool in category theory where we can think of a span as a matrix of sets. So given an element V of V and an element W of W, we can look at all the elements of X that map to V and to W, and we call that XVW. And then span composition, which is given by this pullback, can be seen to satisfy this isomorphism. In other words, the fibers over V and U in a composite are going to be the sum or disjoint union of all the W's of this product. And so this looks exactly like matrix multiplication, although my convention might be wrong. Apologies. This looks exactly like matrix multiplication. And indeed, if you take cardinalities, so if everything is finite and you take cardinalities, you will get literal matrix multiplication. So this is what I mean by compose according to matrix arithmetic, is we're going to land. We're going to define an indexed double functor that lands in a certain index double category of these spans, so that if we decategorify, if we take cardinalities, we end up with actual matrices. So span set is going to be the double category whose vertical arrows are spans and whose horizontal arrows are functions. So this is, my profunctors are still horizontal, but now my spans are vertical. Just want to, it's important. I just want to highly emphasize that. So here's the main theorem, is that for any dynamical system which exposes its entire state, we have an indexed double functor, which I call the representable double functor, into spans of sets. And it's indexed double category of spans of sets, and the codomain here is it sends every set to the slice category. It sends every span to the functor given by pullback, which is also known as the linear functor because it resembles matrix multiplication. So we might think of the slice category as vectors in our vector space, is how we do it if we're thinking of matrices as spans. Then a matrix that's a 1 by n matrix is a vector. So so that's going to tell us the sort of matrix multiplication part of this theorem. And then what it's going to do is, well, we're going to take the horizontal representable parts of this whole story here. So we're going to take the bundle morphisms on interfaces, and that's going to give us a double category to spans of sets, which is a kind of non-trivial theorem that involves a reframing what the double category of interfaces is. And then on systems, we're going to send every system to the set of horizontal system morphisms. So these are the the ones that allow you to change interface into your system. And so when you put it all together, what you can see is if you choose the representing dynamical system to be the real numbers with d dt equals 1, then you get trajectories as fibered over parameters and exposed variables varying in time. If you choose it to be a single point, you get steady states. If you chose it to be a circle, you'd get periodic orbits, and so on. And so this generalizes David's work to a number of other things, and it's actually entirely formal. So pretty happy with it. So I'm just going to end now with some future work. So the theorem suggests that we might be able to solve complex dynamical systems if they have many repeated subparts more efficiently by solving the subparts and piecing them together. So the reason I say many repeated subparts is it's probably extremely hard to solve one system in terms of its parameters. But if you have many of the exact same system, the weight might change. It might now become cheaper to solve that one system freely and then plug in a bunch of them in a complex way rather than the other way. But I don't know if that works. So my question is, does this work? I would love to see more dynamical system doctrines. So I know how to do higher order ODEs, but I don't know how to do PDEs. I don't really know how to do stochastic differential equations at all. So I'd love to see that. I didn't talk about doctrine morphisms, but an example of an approximate doctrine morphism is the Euler approximation method. I would love to see more doctrine morphisms that are actually sort of used in dynamical systems theory. And black boxing functors. So I think index double categories, or generally monoidal index double categories, are a great setting for these kind of systems in general. And I would love to see more invariance of dynamical systems into other sorts, the kind of theorems we've seen across the literature so far. So thank you very much.
All right, thank you. Let's thank David with some silent applause. You can type your claps into the chat or applaud silently. Are there any questions? You can raise your hand or just speak up or type in the chat. All right, I'll ask a question.
As far as,
sorry, go on.
Jazz, if I could ask a question. The restriction that you have to export your entire state space as your outputs.
I'm sorry, James, do you mind if I, 1 second.
Cannot hear you.
Can't hear you.
No, I can't hear you.
Nope.
You should revert to your former state, David.
Whatever we are currently talking. We cannot hear you. Your previous configuration worked.
How about this?
Yes.
There we go.
Okay, sorry. I was getting really bad audio problems. I couldn't understand what you were saying. Could you go again?
So my question was the restriction that the entire state space has to be exported as an output in order to get the main theorem to work. That seems like a really big restriction that is like severely limits the utility of the work. Why not? Hopefully not. But
I don't think it does. So all of the things I mentioned, so it is a big restriction, and it kind of snuck up on me too. The reason it works, by the way, is because if you have the bottom being an identity, you can interpret it either as a bundle map or a lens. And so you get to flip it around one place in the theorem, and it turns out to be that's what makes everything work. But you can always factor so there's a factorization system on Grothendieck constructions. You can always factor a dynamical system into one that doesn't expose any state. Exposes its whole state, and one that doesn't do any updates, but it just exposes something. And so you can sort of crack open any dynamical system you want and say, I want to get the whole picture. I want to expose all the state. So for that reason, I don't think it actually, in practice, has any expressive limitations.
David, can I clarify that that was just on your test object, like whether you're using trajectories or steady states. It's not on your general dynamical systems.
Oh, yes, yes. It's just on it's
okay.
just your representer. Yes, sorry. It's just your representer.
Okay.
Thank you, David. Yeah.
Yeah, that makes more sense, because if it was the other way, that's why I was so concerned. Okay.
Yeah. That would, yeah.
All right. So I think we should be moving on. If there are further questions, we can ask them in the Zulip chat or in other forums. So thanks very much. Let's thank David again one more time.